welcome everybody. Thank you for an introduction, Graham. So, as you mentioned, today we're going to go over a little bit of history uh, and technical knowledge about HTHA. How does it happen? Why does it happen? And also, what are the solutions out there to do this type of inspection and actually prevent any um, major failure or disaster? So moving on, we'll be covering today HTHA mechanism. How does it happen? As I said, we'll also base our knowledge or methods of inspection on the new revision of API 941. A bit of marketing for our product, Olympus HTHA probe kit, as well as the Omniscan X3. What makes it a great combo? Then two study cases. As you may have seen, this presentation is courtesy of a colleague in Dubai, so thank you for that. Conclusion, demonstration, and of course a Q&A session where we will answer all of the questions at the end of the presentation. HTHA mechanism. So first of all, it's really a buzzword these days, but just to be sure everybody we're on the same page. What does that mean? What does it do? So HTHA, high temperature hydrogen attack, also called hot hydrogen attack, is a problem which concerns steels operating at elevated temperature, typically above 400 C, in hydrogen environments such as refinery, petrochemical, other chemical facility, and also possibly high pressure steam boilers. HTHA is the result of hydrogen dissociating and dissolving in the steel and then reacting with the carbon to form methane bubbles. Uh, this causes the fissures and cracking, which are typical of HTHA, and can also be seen in this microstructural image, basically where all the red arrows are pointing. Those are some microstructures, micro cracks. It's difficult to see here, but basically, trust me, it's very small. HTHA is the result of hydrogen service at elevated temperatures, as mentioned previously, as well as pressure. The hydrogen reacts with the carbide in steel to form methane, CH4, which cannot diffuse through steel, so it is trapped there basically. The loss of carbide causes overall loss of strength in the material. The methane pressure keeps building up, forming microfissures that may or may not, depending on the stage, combine to form cracks. So the key factors leading to HTHA, the ingredients to this recipe: presence of hydrogen, presence of high pressure, high temperature, some kind of stress, and also the right ingredients in the material. The stages, let's say, or the severity of the HTHA is divided in 4 stages, basically. From the most minimal one, stage 1, below 50 microns or 0.05 millimeters, all the way up to stage 4, which is basically too late. Connection of fissures to open larger cracks. Some examples of industries where we can find it and some examples of failure as well. Refinery, fossil fuel processing, fertilizer, where ammonia is produced. New inspection approach revised by API 941. There we go. So historically, or traditional ultrasonic methods of characterization were divided into 5 or 4 different ones, basically. You had the method of velocity ratio, where you measure the longitudinal wave velocity and the shear wave velocity in a clean zone of the material, And if the ratio between S wave and L wave changes, that's an indication of HTHA presence. Sorry. Attenuation, of course, if the ultrasound beam has to travel through a colony of HTHA, then the resulting back wall amplitude is going to be weaker. I said 5, basically 4, L wave and shear wave spectrum analysis. So by monitoring the frequency spectrum of the signal that is inside the material, whether it's L wave or shear wave, you can also detect the presence of HTHA. Then finally, conventional single element A-scan backscatter pattern recognition, amplitude-based pattern recognition, spatial averaging, directional dependence, frequency dependence. Okay, sorry, I'm not very common with this one. A combination of these techniques is historically used to assist in characterizing an HTHA from other flaws. It's a screening tool. You can find it. You can discriminate between HTHA and other flaws using these methods. Reliability and repeatability, as stated here, pardon me, are very dependent on the operator's skills. So two-person doing the same inspection might have two different results. Limited data collection for monitoring purposes. Typically, it's those methods require an on-the-spot call, and you have very little data to base your analysis upon. You basically have to have faith in the operator and his reporting. Also, it is very time consuming because the footprint of your transducer is going to be smaller and you have to basically scrub the entire area or zone for detection. New inspection approach. We have different methods that were added to the Article 1 and 4 appendixes. TOFT, time of flight diffraction, phase array, whether it's pitch catch as represented here or pulse echo as represented below. FMC TFM, another method I think that most people or more and more people are getting familiar with, but we'll go over the basic ABCs of these methods in future slides. What do they have all in common? They use higher, right here, highest practical frequency, 7.5 to 10 megahertz, to obtain the maximum detection sensitivity and resolution for micro damage. Time of flight diffraction. What is time of flight diffraction? It's a pair of conventional UT transducer fixed with longitudinal wave wedges, shoes, facing each other and sitting on the same surface of the material. You have the direct path, that is the lateral wave, and the skipping at the bottom, that is the back wall. While scanning, the pair remains at a fixed distance, and typically the result is an A-scan combined with a grayscale image, typically B or D scan. Why would we want to use TOFT? As a screening tool, primarily. Usually the spec will perform a scan on the base material first and then on the weld to have a good understanding of what's going on. It's also common to have two different groups with the lateral wave amplitude being higher and lower on each of those groups, about 50% full screen height compared to 100% full screen height. We'll see what benefit this may bring. Why TOFT? Because it is fast, first of all, then also a very sensitive method. We don't use pulse echo reflection for the TOF technique. We use diffraction, so it's very, very sensitive to smaller voids. Yeah, highly sensitive, and it's also used as a screening method. Well, basically, repeating again. Phased array ultrasound. What is phased array? What's the advantage of phased array? What it offers over conventional UT is that from a fixed position, you can have multiple angles covering a wider area. You can also combine different element input to focus at different depths, given that we are working in the near field. Phased array can be used as a confirming tool. Once the initial screening is done with TOF on both parent and weld, the inspector will confirm findings using phased array ultrasound. Why should we use TOF first? Because phased array will be used at with the appropriate settings, meaning appropriate angle, appropriate focusing depth as well, to have the maximum resolution and sizing capability. So since TOF is limited at finding the exact position but provide accurate depth location, phased array is useful tool to re-examine the components while using the depth information from the TOF finding to focus the phased array beam at that given depth. Basically what says above. Full matrix capture, TFM, this is the latest in those technologies, ultrasound applications. More and more people are getting familiar with this method. The main advantage of TFM over phased array is going to be the quality of the image, the truthfulness of the representation compared to what's actually in the part. Also, as I mentioned, phased array, you have to predict or input a certain focus depth for your inspection to be as precise or as sensitive as possible. With FMC, your entire grid of point is focused, again, given that we are working in the near field. So confirmation tool, just like phased array, as I said, with better imaging. One of the advantage of the Omniscan X3 is that although you can have a 32-128 model, meaning a maximum phased array aperture of 32 elements, the instrument is a PR. So through extended aperture, we can actually generate a true 64 pulsar TFM signal without the need for a 64 element instrument. Why would we want that? Basically to save cost, save money. So this technology with the recommended TFM 64 is available at a lower price, basically. For the purpose of this call and further demonstration, I'm only going to be using one wave set at a time, but you can program more than that and have the input of various wave sets, various TFM modes, basically. To complete this HEHA offering, and I will also demonstrate them later. We also have a complete line of 10 megahertz probes that are pulse echo as well as pitch cache through dual linear arrays. The table from the API, basically, here is the comprehensive summary. So all that I said earlier, TOF, high frequency increased capability for detection of HTHA in the weld. Detection capability is effective. Can detect HTHA in base metal, weld, heat affected zone, as well as the weld itself. Usually effective for length and depth, location, height sizing, but not effective for precise location and sizing, width-wise, perpendicular to the direction of scanning. So basically, if your probes are moving in that direction, the position of the HEHA colony is not going to be super precise using TUF in this direction. Phased array ultrasound, whether we use longitudinal wave or shear wave, 1D linear probe, 2D matrix probe, pitch catch, all those are available. Pulse echo scheme using higher frequency sound increases capability for detection of HTHA in base material and weld. Detection capability usually effective, of course. Can detect HTHA in base material, heat affected zone, as well as the weld itself. Same as for TUF, usually effective for length and depth, location, height and width sizing are also much improved when appropriate inspection setup is used. So again, going back to the previous slides, we use TUF for fast screening to get a ballpark or location of where the cluster might be situated. So we can come later with an additional technique such as phased array or FMC to confirm those findings and also to further improve in terms of width sizing, because we can focus at the right depth, have the right frequency, and so on and so forth. FMC or TFM advantages over phased array. Imaging, I always forget that I can't click. Imaging scheme that involves computation of focused image at every point of the image region. So better imaging, better knowledge of better interpretation of what the flaw might be. And for the rest, it's equivalent, if not better, than phased array. Why would we want to use TUF? Okay, so high inspection speed. Thing to consider, the lateral wave as well as the back wall are basically dead zones or zones where you're blinded by the very strong direct and skipping signals. So keep that in mind when you're screening for HTHA. If it's very close to those surfaces, you might not detect it. So for that reason, as well as a confirmation reason, supplemental technique as phased array or FMC should be considered where damage within those blind zones is a concern. Phased array as well as TFM will achieve their greatest effectiveness in the near field of the transducer. Typical minimum of 32 elements for thicknesses below 1 inch and 64 for above 1 inch. Same goes for TFM, except that we're using 64 elements and 10 megahertz, of course. Characterization capability. With a combination of these techniques, proper characterization between HTHA damage and large fabrication flaws, such as lamination in base metal, lack of penetration, lack of fusion, slag, porosity, inclusions, can be effective through indication location and pattern recognition. One of the most common questions, how do you distinguish HTHA from inclusion or porosities, impurities? It's very difficult. Okay, not gonna lie, it's very difficult. There are some patterns that can be used, which I'm no expert by any mean, but there are some patterns that can be used to determine which is which. Also the location, but that's one of the very big challenge of this this kind of inspection. Difficult to distinguish HTHA-induced cracking versus cracks induced with potential other damage mechanisms from one inspection data set. Again, why we want to use more than one method. With phase array, with Toft, with also proper ultrasonic or phase array instrument, you can record your data, have it encoded, and go back to your data, monitor the growth over time, which is a key advantage compared to the conventional or historic methods. The fundamental principle of historic characterization techniques are still applicable, of course. It's not because we have something new that we have to ditch the old methods. They used to work, they still work. But those methods that I talked about are basically new tools in the toolbox to improve on efficiency, precision, uh, sensitivity, and so on and so forth. So what do we bring to the table? A combination of the Omniscan X3 as well as a new line of 10 megahertz probes dedicated or designed for the inspection of HTHA at their early stage, basically. Dual linear arrays and total focusing methods probes. Of course, they can be used with phase array and TFM as well. If you use the 1D linear probe for pitch and catch, you can use phase array. Greater detection capability, DLA technology, higher gain can be used. Smaller elements equals greater focusing. Higher frequency equals greater resolution. Smaller element improves steering for greater coverage of the well than the has. We'll see in the second study case an example of a weld inspection. During the live demo, I only have 0 degree. Those samples are quite hard to come by, or quite difficult to come by. So we're very lucky to have one today. Higher probability of detection using the multi-technology approach, of course. And also one key advantage of these probes, they're all directly configurable on board the X3. No need for external calculator, no need for shuffling between the computer and shuffling the files between the computer and the instrument. All is on board the X3. So the line of probes in more details, what do we have? With the dual linear array, 828 probe from 1 to 32, 33 to 64. So two 32 element probes for a pitch and catch inspection. They run on a PR unit, of course. We have different wedges with different roof angles adapted for different depth of focusing on the passive axis, different curvatures also of pipes, but through a patented pivot system, we just have one casing for that probe. Traditionally, those pitch and catch transducer use two separate casing or boxes basically screwed on the wedge, and that increases the gap between the two elements. By having all of this encased into a single probe, we can get them closer and have better acoustics. So right, okay, wedge series, yes, of course. We have the focus depth 25 and the focus depth 60, if I'm not mistaken, line of wedges. And they're ideal to cover a range of thickness from 4 millimeters all the way up to 95 millimeters. Irrigation ports and carbides, just like we find on all of our phase array wedges. Mounting hole for scanners, and also curvature is available from 4 inches all the way up to flat. Dual array, the Rex 1 line of probes, 0 degrees. So this design might seem familiar. It's basically the same casing as our 7.5 megahertz corrosion probe, but this one is 10 megahertz first, and also has 64 pulsars and 64 receivers. So twice the elements in the same casing. That means there are twice as small, increasing our resolution with ATHA. Finally, similar to the 10 megahertz Rex one, we also have a 10 megahertz A31 probe as well. Same, similar to the other one because we use the same casing as the regular A31. Actually, I have those two sitting next to me, where the regular A31 might be, by heart, I would say 0.6 millimeter pitch. If we double the elements, the size of the elements is divided by half. So again, it helps with the sensitivity or resolution of smaller defects. You can find all of those details directly from the website. We have a brochure listing all of those details, but you can also reach out to myself or your local sales representative for more info or perhaps demo. The Omniscan X3, so the maximum PRF of the instrument is tripled compared to the previous generation Omniscan MX2. So you can achieve faster inspections without being limited by the instrument. The Tuft menu is a single Tuft menu now, so no need to navigate from one step to the next for a simple Tuft. All is under a single menu. Faster or improved phase array calibrations, also 800 high amplitude range. So the Omniscan X3 is a 16-bit instrument, meaning that there are two at 16, so basically 65,000 counts. The standard mode is the 0 to 200% mode. It can be extended all the way up to 800%. So you do not saturate your signal when scanning with those higher scan gain. And also compared to the previous generation, of course, onboard DLA and DMA calculator. What does the TFM bring? Better flow imaging, so clarity and resolution to smaller defects. Imaging will help with early stage HTHA. Onboard acoustic influence map, the AIM. So you can simulate your inspection before actually going on the part and performing it. One might think, okay, so I can just create my group and test it. True. But the AIM accounts for probe and wedge, material attenuation. It accounts for the type of indication, whether it's round or linear, and also the angle of those reflectors. So you would need either one major demonstration block or a huge briefcase full of them to be able to do what you can do with the AIM software. Visualize TFM sensitivity and adjust accordingly. So going hand to hand with the AIM, you also have an indicator of how strong or how likely you are to get signal in the particular zone that you're inspecting. If you know that you will have a very weak signal, maybe it's better to change strategy and adopt a more adequate wave set. Also, we can create up to 4 TFM modes or 4 different waveset groups to enhance flaw interpretation, detection, as well as sizing. Study case. All theory is good, but it's also good to actually see some results. So the first one was done on an artificially cooked HTHA sample. So basically engineered sample. Multiple hydrogen cracks near block back wall surface. Multiple hydrogen cracks in the first 22 millimeter from the surface. Those were validated through micrographic sample according to micrographic 1 and 2. Dimension of the defects, several cracks ranging from 3 microns to 5 microns. You can see the micrographic sample near the surface on etch, near the surface with the etch, so everything appears way more clearly. So test number 1, TOF, time of flight diffraction. Once the setup is done, so that will be your say basic setup with the lateral wave at 20% full screen height. If you increase the gain, and that's why it may become handy to have 2 separate groups for this inspection, to increase it and have a 50% lateral wave, we can see some diffraction or scattering starting to happen. And if we further increase it to 100 full screen height, now we can actually see where it's located. No filter, again, no filter. Another thing you can do to make it more obvious is adjust the color palette contrast and brightness. So without saturating the lateral wave, we can get the same effect in this location, of course. And again, through higher gain and adjusting contrast and brightness of the palette. Moving on to phase array with the DLA probe, using 32 element aperture and the full length of the probe, focusing at 40 millimeter deep. So before moving on to the actual block, a bit of demonstration of the sensitivity of the probe, comparing it to a block of side drill holes. So by normalizing the gain, you get that type of indication, very small, very rounded. But the overall signal or the overall noise is in the way. We talk about an average of 10 to 15% noise compared to a 40% high HTHA signal. What we can do to compensate for that, we can adjust the color palette, remove part of this background noise from the images. Note that it is still on the A-scan, so you don't delete any part of the signal. It's only visual reference or visual treatment, so that it's more appealing to the eye if there are any indications and where are they located. Same thing here, different location. And location again, so multiple indications with the background noise and without it. and the 2D map, of course, at the end. From phase array moving to TFM, in this case, they use the 10 megahertz A31 with no wedge in contact. So we see from the color map that we are going to be very sensitive right below the probe with a sensitivity index of 30. By the way, this is I think this number has some units, but the way to use it is to compare one mode or one probe to the next and validate that you have the best possible result. Oh, there we go. With wedge, without wedge, pardon me. So as I was saying, if you're in direct contact with the part, you don't lose any sensitivity or any energy or any part of your near field in the wedge. You have a much higher sensitivity index compared to with a wedge. So define the zone in the X3. Validation on the same block first. As you can see, the holes are much rounder and much more accurate to the real life flaw than with the phase array previously. It means that when moving on to the part to inspect for HTHA, you get more accurate results as well. Side view, so scanning from left to right, and a TFM end view. So here's a summary of the same zone viewed by 3 different methods. So going back to the theory before, what we would do is first screen with Toft, adjusted gain, contrast, contrast, and what's the other one? Brightness also to maximize our detection of HTHA cluster or colony. Then go on with phase array or TFM to actually further confirm and size those indications right there. Moving to a weld. First, again, starting with time of flight diffraction. So 50% full screen height, lateral wave, no filter. We see all over the middle here between the lateral wave and back wall. Increasing the gain, increasing the amplitude, it's getting more obvious. So we have to look between, we know we have to look between 12 and 16 millimeter deep inside that weld. So when the time comes to focus, we focus directly in that zone at 15, using a sectoral scan configuration like that with the 828 dual linear array probe. We can go back on the block, confirm our sensitivity, and then moving to the inspection itself. So with the calibration being done on those sidewall holes at 35.5 dB, we get that type of very weak signal through either scanning gain or analysis gain, software gain, whatever you want to call it. We can increase it and make this trail of indication way more obvious. Okay. So you can analyze it from one to the next and again. Comparing this to TFM using the A31 linear probe, using TT or shear wave, basically pulse echo method, sensitivity index of 20. So you see that we are less sensitive with an angle beam probe like that than previously when we were sitting directly on the part firing at 0 degree, which is quite normal. Validating on the calibration block once again. Then moving on to the inspection. Some visual or color filters can be applied to make this a little bit more obvious. But here is our trail of HTHA, like we saw with phase array. Confirmation with Tuft, validation with either phase array or TFM. In conclusion, Tuft detection capability is usually a very effective tool. Tuft is primarily a screening and exploring tool. It's limited for single side access, so pipe to component, for example, because if you want to inspect a weld, well, you need each transducer to be sitting on either side of that said weld. Phase array focus needs to be adjusted carefully with information provided by Tuft. Phased array, DLA 10 MHz probe and 828 probe provide the best SNR. TFM is another confirmation tool that can provide better resolution by the technology that we use. TFM frame of wave modes or wave sets need to be selected carefully. Going back to those slides here, we have a linear probe, we have a shear wave wedge, must be, well, you can select L wave. You may not have the best results in the world, of course. TFM is no magic, so that's why having a tool like the AIM helps in preparing your scan plan upfront of your inspection. And in conclusion, so the fundamental principle of historical characterization techniques, backscatter, signal pattern recognition, FFT analysis or frequency spectrum analysis, velocity ratio, they used to work, they still work, and they can assist with those updated techniques or innovative techniques to improve capability and confidence for characterization between HTHA and other damage mechanisms. Now the fun part. Moving on to the live portion or demo. So I have set up 3 different groups on my Omniscan X3 to tackle first the phase array portion of the demonstration. I don't know if you can see, but we have a block here that has very tiny holes, basically simulating what we can find in those type of inspection. And also, as a bigger one, we have another sample that is cracked pretty badly. So we will validate what's in there, what can be found, and how good of results we can achieve. Starting with the regular probe, because we have to have a baseline. And you can see that I'm using phase array, 0 degree probe and wedges. But instead of creating a direct 0 degree linear scan, and that's a personal preference, I prefer to use a range of angles using L waves from negative 30 to plus 30 degrees. I find that it does a very great job, especially on the sample that I have today. So a little bit of couplant or water on the sample, moving it up and down, trying to find the spot. That sample is quite thin. So if you look at the S-scan, well, those are the type of result we get with the 5 megahertz 32 element A31 probe using a 32 element aperture, focusing at 18 millimeter deep. Okay, so changing this probe now for the 10 megahertz 64 element version. There we go. Cranking up the gain a little bit. So straight away, we can see that the holes, side drill holes, are more well-defined, well-rounded, and also we can count more of them. As with the previous probe, they weren't resolved one from the other. Now from here, moving to the 828 dual linear probe. Element 1 is this one. A little bit more water. Where is it? Oh. So just have to maximize it. Apply some gain. And again, we have great results using this probe. So that's all good. Everybody can do it on side drill holes. What about the real part? Moving on to the next one. So I'm going to do the same progression, starting with the 5 megahertz 32 element one, which is this one right here. Yep. Now we are a bit hot because I moved those parts. Looking at the S-scan as well as the B-scan that is scrolling at the bottom of the screen, we can actually see, well, of course, that's a blister right there, but we can actually see the connection in between and some granularity or some isolated defects, which may or may not be an HTHA colony. Moving to 10 megahertz. Again, can lower the gain a little bit. So straight away, I'm in the same spot with the same blister on top, the same indication underneath. We can see a clear difference in terms of resolution compared to the 5 megahertz. Everything is more crisp, everything is more well-defined, well-rounded. Especially here. Finally, the pitch and catch. So moving to the DL dual linear array probe. Lowering the gain a little bit. Just look how beautiful that is. So we have that blister. We actually, what we could see as a single red blob with the 5 megahertz, now we can see all of the detail with the 828 and the 0-degree wedge. Actually, that probe was designed to do angle beam inspection, not so much 0-degree. So perhaps I'm helping my case doing a sector like I'm doing, but it was really designed to do weld inspection, going from low angles to high angles. I think we're doing a pretty decent job here in this area where clearly we have a problem. So that is for phased array. We also spoke about TFM, so I will demonstrate this one as well. Starting with the 5 megahertz A31, and you might wonder or ask why a 5 megahertz A32, why not 5 megahertz 32 element, why not a 10 megahertz 32 element? Well, simply because the 5 megahertz 32 element is our go around common probe for Weld Series probe that we use on a various applications, on a wide variety of applications. So you are likely to find it at your place as well. And also, we want to today show the improvement 10 megahertz can bring over the standard probe, and also smaller elements, actually half the size in this case. So actually, I didn't show the little tiny dots before. Here we go on the block with the side drill holes. I have to stay in my sensitive zone, sensitive area. So depending if I move left to right, I'm going out of my sensitivity area, but when I'm in there, the side drill holes are pretty well defined. And if you're wondering at the top here what's happening, it's because my wedge is actually wider than the block that I'm using. So there's water dripping on either side and it's causing all those ripples. Now moving to the block, lowering the gain a little bit. We can see that it's an improvement over the pulse echo phased array for sure, but I think we can do better than that. Still working in the same area over the same indications. So from this probe, I'm going to go ahead and select my 10 megahertz. Also, in the presentation you saw in the case study, Sabri and his team did not use any wedge on the probe. Of course, that helps transmitting all this near field inside the part as I mentioned. But since probes are quite expensive, and you're very likely to use it with a shoe attached or a wedge, I figured that it might be good to actually demonstrate this with a 0-degree wedge rather than without. Again, going on the same block with the same water dripping on either side. Left to right. Just maximizing it. There we go. Looks pretty decent. Now if we move on the part, drop the gain a little bit. Same effect as before when comparing phased array pulse echo between the 10 megahertz and the 5 megahertz. Now with TFM, the main advantage of this probe over the other probe, smaller elements, higher frequency, and also now we have a 64 element probe compared to a 32 with the other model. So I'm actually creating a full 64 TFM right now, which also helps and improves on resolution as well as sizing, right? And just like that, that's it. Okay, so that was a presentation. Thank you, everyone.